Hello everyone. Today is August 30th, Saturday. It's your host, Samuel Annie, here to introduce a super interesting, trending article from the archive. Get ready, because today we're diving into the world of robot brains. It sounds like something out of a sci-fi movie, right? But it's totally real. The title is Learning Primitive Embodied World Models Towards Scalable Robotic Learning. The curl is chancecolon//may-22.gatil.io/primitive-world/. It's long. So let's get into it. Have you ever wondered why it's so hard to build a robot that can do everyday chores like us? Like picking up a cup or folding a towel? Well, a huge problem is the data. To teach a robot, you need to show it tons and tons of examples. Getting this data for robots is super expensive and difficult. It's not like scraping text from the internet for an atlas. We need real robots interacting with the real world. And every situation is a little different. Current AI models try to learn a whole task at once by watching a long video of it. Imagine trying to learn a whole dance routine just by watching a chore movie. It's really hard, right? The AI gets confused and can't predict what will happen far into the future. This has been a major bottleneck, stopping robots from having their "oh my god" moment. So, this paper comes in with a totally awesome idea. Instead of making the AI predict a long, complicated video, they said, hey, let's break it down. They proposed something called Primitive Embodied World Models, or PEWM for short. The main idea is that any complex action is just a sequence of super simple, basic movements. They call these basic movements primitives. So, instead of learning the whole task of pick up the yellow tape measure, the robot learns a sequence of primitives like move the gripper to the tape measure, 2, close the gripper, and 3, lift the gripper. See? It's like building with Legos. You combine simple blocks to create something amazing. By focusing on these short, simple primitives, the AI can learn much more efficiently. It's way easier to predict what happens in the next second than what happens in the next minute. This makes the whole process faster, and it doesn't need nearly as much data. This framework is so cool because it works like a brain. It has two main parts. First, there's a high-level planner, which is like the cerebral cortex. This is a vision language model, or a VOM, that understands the human's instruction and breaks it down to a sequence of primitives. Then, there's the world model, which is like the Scalable. This part is responsible for fast, reactive control. For each primitive, it generates a short video of what should happen. It's like the robot imagining the next step before it does it. And because it's only predicting a short clip, it can do it in real time, at about 12 frames per second. That's fast enough for smooth, low-slope control. Now let's talk about some amazing applications. First, think about video conferencing systems like similar tunings. With this tech, you could have a virtual assistant robot in a meeting. You could say, hey, can you write down the key points on the whiteboard? The AI would break this down into primitives, like pick up marker, move to board, write letter, and so on. The system could then generate a video of a virtual robot arm, doing this in real time in the conference, making remote collaboration feel more interactive and physical. Second, let's consider interactive, learning content. Imagine a chemistry class where students are learning improv. They could instruct a virtual robot arm to conduct experiments. For example, a student could say, carefully pour the blue liquid into the beaker. The PEWM system would generate a realistic, physically plausible video of the robot doing exactly that. If the student makes a mistake, like mixing wrong chemicals, the model could simulate the dangerous outcome safely and fair. This makes learning way more hands-on and engaging. And third, this is huge for smart factories and logistics. Right now, factory robots are usually programmed to do one specific, repetitive task. If you want to change the task, you often need to reprogram it completely. But with this primitive-based approach, robot could learn to assemble a new product on the fly. A manager could just give it instructions like, pick up the screw, insert it into the hole, and tighten it. The robot would already know the primitives for picking, moving and turning, and could combine them in a new way to complete the task. This would make factories so much more flexible and efficient. So, how does this compare to other technologies? Well, a lot of recent research, inspired by models like Sora, tries to generate really long videos to predict the future. But this is super slow and non-potentially expensive. It's not practical for a real robot that needs to react quickly. PEWM, on the other hand, focuses on chores and predictions, making it incredibly fast and efficient. It's the difference between trying to write a whole novel at once versus writing it sentence by sentence. Then there are the in-to-mind models, which are often called vision language of law models. These are kind of like a black box. You give them an instruction, and they spit out an action. If you don't really know how they made that decision, the PEWM framework is modular and interpretable. You can see the plan, the sequence of primitives, which makes it much easier to understand, debug, and trust. Plus, this paper showed that the method works on new tasks without any extra training, something that law models really struggle with. In conclusion, this paper is so important because it offers a practical and scalable way to build more gen-purpose robots by breaking down complex tasks into simple, reusable primitives. It's like giving robots a set of fundamental building blocks for intelligence. This paves the way for robots that are more adaptable, efficient, and better at working alongside us in our daily lives. It's a huge step toward making truly general embodied intelligence a reality. That's all for today. I'm Sanel Kaini, and I'll be back next time with another exciting paper. Bye-bye.